Welcome to the Rancho Mirage Library and Observatory. My name is McLaughlin. I am the astronomer here, and what we'll be doing tonight is we're going to be talking about Jupiter. Appreciate you all being here. It looks like a few of you, again, weren't so enticed by democratic debates that you were able to come out here tonight. I appreciate that. I will note there is a small note on politics in here. It has to do with a very specific spacecraft. You'll understand when we get there. But again, appreciate you being here at this point. Also have a few other things to note, and that is we have a special thanks to our Library and Observatory Foundation. It is through our foundation that we're able to offer these events here for you. Again, free of charge. It is through that particular foundation that we get that funding for these events. So a special thank you to the Library and Observatory Foundation. Another thing worth noting is we just had back in July the 50th anniversary of the Apollo 11 landing, and we were really excited to celebrate that with many people here in this room. We also are really curious where people were at that time, so we have a nice little table back in the back of the room there where you can fill out a little slip and let us know where you were, and there's a big giant map over that where we are actually putting markers up there to show where people happen to be at that time. So we're really interested just because we find it interesting. So with that said, another really interesting thing, of course, is Jupiter. Jupiter, again, is the largest and most massive planet in the solar system. It's a fascinating place, one that actually has a very different makeup than what we have here on the Earth. It is known for having really dramatic, intricate cloud tops that span the entire globe of that world. It is, again, the most massive world. It is actually more massive than all of the other planets in the solar system combined. It is circled by many moons, well over 60 moons, actually over 70 moons even, and it is, of course, famous for its storms and its stripes. The one storm in particular likes to rotate into there. It is that great red spot. We'll talk about that as well as some of the lesser known things, including a very faint, very dim set of rings that actually are around this big planet. They're highlighted right there. Yes, we're going to spend some time talking about this world and its surrounding region in great detail. So to actually get in that detail, let's rewind in history and talk back right about where everything was really getting started with regards to even its name. Its name comes from the Roman god Jupiter. This deity is essentially the Roman equivalent of Zeus. It's a little bit more complicated than that, but that is essentially the case. And so that particular name is worth noting, but of course it has been seen by all sorts of different civilizations throughout history, and so there's a lot of different things associated with this particular world. In fact, in the Eastern zodiac, it is through Jupiter that we're actually able to get those fun year names that you hear in the Eastern calendar. You know, when you talk about, say, the year of the dragon, the year of the pig, so on and so forth, those come from actually the Eastern zodiac, and in particular, which constellation Jupiter happens to be in that at the beginning of that particular year. Because Jupiter's orbit is about 11.86 Earth years, it means that it works out really well for 12 different constellations, so it works out quite nicely for that. But it is also believed by some to actually be associated with the phenomenon that is referred to in Judeo-Christian records as the Star of Bethlehem. And one person in particular was really interested in looking into that. That person was Johannes Kepler, who when he was actually looking at the motions of everything in the sky, he, for one, actually happened to be one who actually did believe a bit in astrology, and so when looking back, he was wondering what would people who believed in astrology be looking for the birth of a king. What he actually found was that Jupiter, again, he found this by hand after making observations and then backtracking them, calculating by hand exactly where Jupiter would be back thousands of years, or over 1,000 years, found that Jupiter made a little bit of retrograde motion right around a very specific star called Regulus in the constellation of Leo the Lion, and that particular thing to him was a note about, well, this is the kind of motion in the sky that might have triggered some people to say a king would be born, and that was really his notion of what the Star of Bethlehem would be. So this particular world, Jupiter, it has been viewed and has had a lot of really interesting things in ancient times and again on into the Renaissance. And contemporary of Johannes Kepler, Galileo Galilei, he was actually the first to point a telescope at this world. He was the first to point a telescope really deep into the sky at all, and he spotted some really interesting things, including a set of its 4 largest moons. If things work out well tonight, we can hopefully make our way up to the telescope after we're done here and actually maybe get a chance to see these moons ourselves. They are now referred to specifically as the Galilean moons, specifically because of Galileo. But we'll talk more about those later. But they were really important in actually really showing that objects out in the rest of the solar system, they don't necessarily revolve around the Earth, which was the prevailing theory by many at the time. So the work of these two gentlemen was among the most key in really driving home the notion that the sun was at the center of our solar system. That is the heliocentric model. And in this setup, Jupiter is the 5th planet out from the sun, orbiting the sun at about 780 million kilometers, or about 5.2 times the diameter of the Earth's orbit. So it is 5.2 times further out from the sun than the Earth is. All right, so that is all great and well and good. Well, I've referred to this as a gas giant. It is worth understanding what a gas giant is, and basically, it's a planet that's mostly made up of hydrogen gas. That particular note, though, it gets a little more complicated, but mostly hydrogen, quite a bit of helium too, but again, hydrogen will be the most dominant thing there. And it's also possible that there would be some kind of solid core at the center. It's hard to tell specifically. We can only make very specific gravitational measurements by sending spacecraft around this object to try and probe the deepest depths of this world. And if Jupiter has such a core, it's going to be quite massive. It would be more massive than the planet we're standing on, again, about 15 times the mass of what we're standing on. But you shouldn't really think of that as the true surface of this world. That is more like the seed from which this planet would have grown. Again, a bit more on that as we get going, and it is worth coming back to that notion of a gas giant. The idea that this planet is primarily made up of gas is a bit of an oversimplification. It's made up of hydrogen and helium. Here on the Earth, it's nice and gaseous. But things get a little bit weirder when you increase the pressures and temperatures deep inside a world like this. So to actually really talk about that, I need to introduce a little concept called a phase diagram. What is a phase diagram? Well, it's a fun little picture that helps us understand how a material behaves in certain conditions. For example, let's use a little bit of help from a really fun webcomic done by a man by the name of Randall Munroe. He makes the XKCD comic, which is very science-oriented, and it's a lot of fun for nerds like myself. But he was asked a question: could you actually float a submarine deep into Jupiter's atmosphere? Well, that's a wonderful question, and to really describe how a phase diagram works, he gave a great one with regards to a submarine. Let's see, submarine phase diagram here. If we have pressure on the left axis, that is, pressure increases as we go up in this picture, and temperature increases as we go right in the picture here. Well, if you have low pressures and temperatures, you have a submarine, right? Well, if you increase the pressure, even if you do that here on the Earth, you dive too deep, eventually pressure gets such that the submarine itself will get crushed by that pressure, and you end up with a shipwreck. So that would be very bad, as would heating the submarine up so much that it would start melting and give you a nice molten shipwreck. So it is something that is pretty easy to understand. You want your submarine at low pressures and temperatures. If you increase temperature too much, it melts. If you increase pressure too much, it gets crushed. If you do it in just the right way, you might get everything happening at once, referred to as a triple point. Anyway, this is a lot of fun stuff, and the specific question of whether or not you could actually float a submarine in this particular world's atmosphere, well, I'll let Randall Munroe explain that. You'll have to go check that on his website there. But it is a fascinating read, by the way. Anyway, we want to use this phase diagram to understand what's going on inside Jupiter. And unfortunately, this phase diagram have the axes switched. Now temperature is on our left axis going vertically up, you increase temperature, and going to the right, you increase pressure. Now, they say log pressure and temperature because we're going at factors of 10 times as much, so each number up is 10 times the pressure or temperature on each axis. Anyway, how are we actually going to understand this? Well, here on Earth and above the cloud tops of Jupiter, yeah, hydrogen's going to behave a lot like a gas. However, this is the path we can expect to go down, this red line, as we go deeper into the atmosphere of Jupiter. Eventually, that gas gets heated to pressures and temperatures that the distinction between a gas and a liquid is kind of lost, and it's then referred to as a supercritical molecular fluid. So much of an interesting material that you really can't say this is a gas, and you can't say this is a liquid. The conditions for hydrogen at that point really make that distinction completely moot. That is why this line going up here just ends, because once you go beyond that line over into this area, yeah, there isn't a good distinction. So, if we keep going down that path, though, eventually we end up with a different kind of liquid, a metallic liquid. This is something we see here on the Earth with not hydrogen, but instead, say, with mercury, or if you take gallium and hold it in your hand, it'll melt. There's some liquid metals you'll run into here on the Earth, and they conduct electricity, they conduct heat. They're very interesting materials, but making metallic hydrogen has proved to be very, very difficult. Liquid metallic hydrogen here on the Earth, well, when it was first made, no one believed them that they made it, so they had to make sure they reproduced their results. And this involved diamond anvils and all sorts of really impressive techniques to really make pressures high enough to actually make this substance. That is how extreme this is. A significant portion of Jupiter's interior is made up of this stuff. So, just to give you an idea on how extreme the things are deep inside Jupiter. Another thing that can happen potentially down there is there could be a point at which the material is supported by what is called electron degeneracy pressure, or there could be a core there. But that electron degeneracy pressure, it is a very weird thing. It's from quantum mechanics. Let's take one quick moment to talk about it. It is based on the Pauli exclusion principle, or PEP as it's sometimes abbreviated. Basically, all it's saying is two things like electrons can't occupy the same space. Say, for example, we want to actually treat you all like electrons here. There's a number of seats in here, and if we say that no one can share a seat, then if we get a certain number of people in here, well, then all of our staff feel quite a bit of pressure because we need to actually make sure that we get more seats. So in a similar way, you only have so much room for electrons as you increase the actual density of those electrons in a place like this. So again, this particular mechanism is what gives electrons their orbitals. You might know the Bohr's model of the atom, where you see the little electrons zipping around the nucleus. Well, the way in which electrons zip around a nucleus are very specific, and they're very distinctly related to the energy state of those electrons. So again, you can't have more than one electron in that same exact set of circumstances, so you end up with a set of pressure from that. And this particular mechanism is what actually manages to support the cores of dead stars like our sun that form white dwarfs. They are seething hot masses of carbon and oxygen that are so dense that they need this to be able to keep their structure. Otherwise, they would collapse either into a neutron star or a black hole. That is how important this particular mechanism is, and it may very well be at play deep inside Jupiter, especially if there is no solid core. All right, so lots of technical terms there. Let's go back and take a look at just a nice diagram because it's a lot more fun to talk about here. Yeah, so here we have the large section of the interior of Jupiter is that metallic hydrogen, and above that you end up with that weird phrase I mentioned, the supercritical molecular fluid up above it. Here, yeah, they wanted to say liquid, but it is really more complicated than that. And then eventually you get up to where you have that nice, just normal gas that we know of that helps make those nice cloud tops, which let's go ahead and actually take a quick look at, wow, that's playing a lot faster than it did before. All right, that was the Voyager blue movie, as it was referred to, because these were all taken in a blue filter, and while it played so fast, you can't see the particular details of what's going on there. What you can see is, oh my gosh, now, I don't know why that's playing so fast. It didn't play that fast last time we checked. But you could see as that was going the different rates at which everything was moving, the actual motion of the great red spot, and all these different things. It is a really interesting video to see. Each frame was taken 10 hours apart, because that's how long it takes Jupiter rotate once on its axis, allowing us to see the great red spot staying essentially stationary. Here it is, one more fast time. Whee! All right. So that is the Voyager Blue movie. That, again, was from quite a number of years ago. We've got some really nice data since then using a number of different spacecraft. And let's see, this particular image is from the Cassini spacecraft. It was a spacecraft intended for Saturn, and it spent over a decade there giving phenomenal imagery, but in order to get there, it needed a little bit of an energy boost from Jupiter, and so when it was getting that boost, it took this wonderful image. And one of the things I always love pointing out to people in this particular image is what you see here with the great red spot. You can see these funny vortices shedding off of the edge of it. The material there moving in a very specific direction. That particular set of vortices is very scalable because it's very similar to what you see when you see a flag waving. When wind blows past a cylindrical object, it sheds vortices behind it, and that is what drives a flag to wave. Here it is at a scale that's larger than the planet we're standing on. So it's a really neat thing to actually see this thing that scales not only down to the level of flags. You can actually take this down to mechanisms you can hold in your hand. It's something really important to actually what they call hot wire anemometers, ways of measuring wind speeds using a wire that is heated up. You have to worry about shedding of vortices even on just a wire. It scales up to bigger than this planet. I just love that fact. Anyway, moving right on to talk more detail about that surface. Again, when I say surface, make sure you understand I mean surface. It is the cloud tops of Jupiter that we really are talking about because, again, even if we're talking about something like the sun, there's no solid surface for the sun that we're really referring to. Instead, we really refer to the area that we can see for things like this. Because, well, it makes a lot more sense and makes a very good reference point for us. So when we're talking about Jupiter's surface, we can note a few things. Again, there are those zones, those lighter regions, the belts, the darker regions, and we can see them quite readily, especially in images like this. This one's going to be a color-enhanced image from the Juno spacecraft to show a bit more contrast. But you can see those big, bright white regions, as well as the belts, those darker regions going off on either side. They are beautifully intricate when you get nice and up close to them. And in fact, those particular zones and belts, they actually have a bit of an analog here on the Earth. They're a lot like the prevailing winds or the jet streams here on the Earth, and they actually do get divided up in counter-rotating directions, as we saw in that blue movie from Voyager. The interesting thing about these things, though, is they only go about 3,000 kilometers deep. The radius of Jupiter is close to 70,000 kilometers, so it's a big difference there. But beneath these, you actually have that liquid metallic hydrogen and other material there that's really moving not as a solid, but really it's referred to as rigid body motion. It's like it's static as it rotates, and that's a really important thing for understanding what's going on in this particular atmosphere and for the dynamics of how the weather on Jupiter really works. So, what do we see there? Of course, well, we see a lot of various storms, and we also note that the poles look incredibly different than the lower latitudes, the area near the equator where you have really distinct zones and belts. Up at the poles, we see some really fascinating stuff. For example, this infrared image shows a nice set of polar vortices around Jupiter's north pole. It has one in the center and basically a nice square of 8 storms right around it, all rotating in their own way, actually all working in a really interesting dance around this. And this square is pretty persistent. And in fact, this particular planet has a square at the top and a pentagon at the top, at the bottom, at the south pole. You can see about half of it there in this image that is the same as this, but it's just brightened up so you can see that detail. This is actually pretty normal for gas giants. Saturn has a hexagon at its north pole, so this is something we've actually started to become expected for worlds like this. So it'll be interesting if we ever get a close look at gas giants outside the solar system to see if we see any similar nice geometric patterns. But it is a fascinating thing to see something so regular in a world that is literally a big ball of fluids. So it's a wonderful thing to see. Another thing that's neat to see is to actually take a quick flight through to a very specific place. Now, again, altitude here is really based on your height above the cloud tops or proximity really to normal atmospheric pressure here on the Earth. It's a handy thing to do. So let's go ahead and fly on in here. And as we do so, it is nice to see the temperature rise. We are hanging out right around here. So this is quite a bit warmer. And you'll notice it's gotten a lot redder here. That redness is worth taking a closer look at. This is that massive storm on the surface of Jupiter. This is the Great Red Spot. It is still a very large storm that is worth taking a lot more of a focused look at. So, as we do, it is worth again, seeing a nice full-scale image here, again by the Juno spacecraft, slightly color-enhanced to show more contrast. But again, it is a gigantic storm that is in the southern hemisphere of Jupiter, in case that wasn't apparent. It is actually rotating counterclockwise and is larger than the planet we're standing on in diameter, this particular direction being the main area there, but it has been shrinking. In fact, it was quite a while ago seen as being on the order of 2 to 3 times the diameter of the Earth. But even since the time of the Voyager spacecraft, it has dramatically shrunk. North to south, it's shrunk by about 1/8 since that time frame, and east to west, it has shrunk by about 1/3. That is a significant decrease in size, especially when we start to consider some other factors about it. Now, let's note the red color there. Again, that red color is mostly going to become, or it's essentially going to be coming from the clouds, or the chemicals in those clouds. But the chemicals in those clouds, it's more a question of how they get there to make it red. Is that coming from material that's being dug up from underneath, or is that material that, as it's being brought up to high altitudes, it's interacting with ultraviolet light and turning red? There are those mechanisms, among maybe some others, that are good candidates to really describe how the red spot gets its color. The specific details will take more observations and experimentation to really try to understand. Now, I mentioned that we've noticed this particular storm shrinking, and that's not over a small time frame. It's over a very large time frame, because we know this storm is at least 150 years ago, but we have a couple of observations dating back to the 1700s and the 1600s respectively that seem to suggest it could have been actually around for at least 350 to 400 years. However, the fact that we have a big gap from the early 1700s to more modern times, that makes some people wonder, well, maybe it actually went away and came back. Something we will not have a definitive answer on probably ever, but nevertheless, it is worth noting that this particular storm is quite persistent. We'll be interested to see if it actually remains so persistent, because again, it has been shrinking quite dramatically in not a very long time. Again, for something that is larger than the planet Earth, shrinking by a factor of 1/3 in one dimension in our lifetimes is pretty short time frame. So anyway, let's also note how deep this particular storm goes. It's worth understanding that. So really, if we want to understand that, we got to take some data using some microwave receivers, and these are from the Juno spacecraft, showing a nice surface image here. And using different bands, they're actually able to look deeper into the clouds of Jupiter, seeing that right at the top of it, it's actually quite cool underneath, but deep underneath there is a very hot spot that is actually providing a significant amount of warmth, which is likely driving the storm itself. So how does it drive a storm itself like that? Well, this is something we see here on the Earth all the time with regards to hurricanes. You actually have warm oceans that actually drive the actual storms to actually fuel them, giving them energy to actually fill up with water and move it around and cause quite dramatic rains. So it is in many ways a little bit like a gigantic hurricane. But this particular one is nice and persistent because unlike hurricanes here on the Earth, there is nothing for this particular storm to really collide with. So it can just maintain its actual energy flow up into it and actually keep on going. So it's a fascinating storm that has persisted for a long time. Now, I've mentioned the Juno mission quite a bit. This particular mission is a really fascinating one. It arrived at Jupiter back in 2016, right on July 4th. It's a nice patriotic spacecraft. And it was actually slated to end in July of 2018. Fortunately, it was actually had its mission extended to 2021 because it actually used a slightly different orbit than was originally planned, and that allowed it to save a lot of fuel. That orbit, though, is really special. It provides really interesting views. If we're looking at Jupiter, it is in a very highly elliptical orbit, meaning if Jupiter's over here, this particular spacecraft comes in really fast and zips by it and shoots out to the side. And the reason for that orbit comes from particular things around the environment of Jupiter, including a lot of radiation. We'll talk more about that later. But we end up getting really nice close-ups of some features here on the, again, quote, surface of Jupiter, where you can actually see, in this particular case, a nice vortice, a nice storm coming a bit close to the red spot and actually peeling off parts of the material there. And so as Jupiter went over the North Pole and down to the south, you can see it's actually moving away from it in this particular view. But these are a wonderful set of slightly color-enhanced, again, really more contrast-enabled images to help us see all these nice details here. So that is really what the Juno spacecraft is doing. It isn't doing what some other spacecraft will be doing. That is, it isn't spending time off the surface or away from the surface of Jupiter looking at the moons of Jupiter. There are a lot of moons of Jupiter, by the way. It actually has, at its current count, at 79 moons. They range in size from a few kilometers to, again, being larger than the planet Mercury. These are a huge range in sizes for moons. And again, of course, Galileo was the one who found the first four, the largest of them. Again, they're named after him now as a group, the Galilean moons. And they are actually individually named after the lovers of Jupiter, again, the Roman god. And their names include Io, which is a very dramatically volcanic world because it's hanging out quite close to Jupiter. And so this might be what sunset could look like a bit over Io there. You can actually see some glowing regions from all of the volcanic activity there. And this particular world, it's a little bit washed out here now. That was not washed out earlier. All right, so this particular world, it has what you kind of expect of a world. It has a iron sulfide core. It has a rocky mantle, and it actually has a lot of lava being ejected from it. And sometimes it does so in really dramatic ways, where you can have plumes of material being shot up hundreds of kilometers over the surface. This particular image, I believe, is from the Cassini spacecraft. As it was, again, on its way to Saturn, it got this really nice view here. But yeah, that is no small plume there. So the actual temperatures inside really make it nice and dramatic. So how does it end up with such dramatic temperatures inside? Well, because the orbit of Io is not exactly circular, meaning it gets a little bit closer and a little bit further away from Jupiter as it orbits around, and different shifts in that actually cause the interior of that moon to actually get stretched and rendered in such a way that it generates heat and that heat translates into volcanism. All right, so this is another view of that world. This particular view really helps show how it gets a nickname that one of our docents loves to refer to it. Our docent and library and observatory commissioner, she likes to refer to this as the Halloween moon because of the nice bright oranges and black features there, because of all the volcanism and all the sulfur deposits everywhere and all that dramatic stuff going on in this little world. But it is also joined by another world that is highly influenced by those tides. This is Europa. Europa actually has a really dramatic shape to it. It is covered in a nice thick layer of ice, and that thick layer of ice is sitting on top of a massive ocean. This particular ocean may not look like much here, but it is expected to be actually larger in volume than all of the Earth's oceans combined. Actually on the order of around 2 to 3 times the volume of all the Earth's oceans combined could be residing in a nice shell underneath this particular icy crust. It is a fascinating world, and it looks absolutely stunning. It looks a lot like a cracked eggshell with all sorts of cracks going all through the ice that are colored really dramatically. So we want to take a closer look at this particular world, and I'll talk more about that aim to get a closer look here in a few minutes. But moving out, we have Jupiter's largest moon and the largest moon in the entire solar system, Ganymede. It is also expected to have a saltwater ocean beneath its surface, but it is much deeper beneath its surface than Europa's, so it's kind of outside our reach by any technology we can think of at the moment. Maybe someday we'll take a closer look at that, but it will be quite a while before we do so. And this particular moon has some really neat features. It, unlike Europa, has a much older surface that looks much more stable. You can see a lot of craters that have been able to persist for a long period of time, as opposed to Europa, where you find almost none. So that surface of Europa seems to be more dynamic. All right, so after Ganymede, we have Callisto, which is the furthest out of the 4 moons, taking 16 to 17 days to orbit all the way around Jupiter. And it also likely has a little bit of water beneath its surface that's a bit difficult to get to. So again, it will be a long time before we ever think about trying to get to that particular ocean. But it also, like Ganymede, is covered in many different craters and is very specifically, old-looking because of the fact that those craters seem to persist quite a long time. All right, so I mentioned that we want to take a closer look at some of these worlds, and the way we want to do that is with the Europa Clipper and JUICE. Europa Clipper is one that actually is being developed by NASA, and JUICE is the ESA's, that is the European Space Agency's, Jupiter Icy Moons Explorer. They really had to try for that acronym, but nevertheless, it works out well. JUICE, I guess. All right, so the Europa Clipper actually aims to orbit Jupiter, but in such a way that every orbit will bring it by Europa. It'll be a very similar orbit to what we saw with Juno, but this particular orbit will again give us a good chance to take a lot of closer looks at it. And this particular mission is very unique in the missions that NASA is working on, because this particular mission has been largely pushed by Congress, specific members of Congress. And I told you I'd come back to politics. This is the thing. So this is something that has been a weirder journey to actually get launched. It's actually expected to launch in the mid-2020s, as with the Europa, or as with JUICE, but the details still have yet to be worked out because, again, politics. But the mission itself, it might fly on a Falcon Heavy, or it might fly on the Space Launch System, the SLS. And if you aren't familiar with those, how about a shameless plug? Come to my talk next month on October 10th, because we'll be talking about the future of space exploration and talking about both those rockets. All right, shameless plug over. Yes, the spacecraft itself will be an interesting one. It may or may not include a lander. We don't know where they're going with it because, again, politics. But we have a lot more certainties with regards to JUICE. It is actually going to, once it arrives, wander between Europa, Ganymede, and Callisto for the most part to get a lot of different views of those worlds. But it's going to take a while to get there. It's expected to launch in 2022, and this is the route it expects to take. We launch out of Earth, and we get a nice, interesting orbit there that will allow us to get slung-shot by the Earth, get a little extra energy, and then a little more energy from Venus, and it will get us a little ways out there. Not quite far enough, but it'll get another little nudge from the Earth and a nudge from Mars, and still not quite enough to get out there. So it's going to come on back into the inner solar system, looking for a nice little tug from the Earth again. All right, and now it gets just enough to get out there to Jupiter's orbit right around the time that Jupiter will come up from behind it, seemingly slowly, but again, it takes a lot of effort to get that high up above the sun, and then Jupiter will come in really quickly and scoop it right up. And so that is the projected path of the JUICE mission. It is going to take it until 2029 to reach there. So launch in 2022, get there in 2029. That takes a lot of effort. Now, going back to the Europa Clipper, I mentioned the two options for its launch vehicle. If it uses the Falcon Heavy, it can launch sooner. And if it launches sooner, then it would probably take a route like this because the Falcon Heavy is not expected to be as strong as, or as have as much delta V, as they say, as the SLS to give it a straight boost there. If we wait an extra year into 2023, we'd be able to send it to Jupiter with a single boost from the SLS, in theory, if it gets done in that time frame. And that particular setup, again, would get it there before JUICE, allowing it to start its science mission ahead of the other one, giving us actually a longer span of data, which is nice, but it doesn't come without a price tag because the SLS is expensive, very expensive. Some estimates say you might even be able to get a second mission out of it if we use Falcon Heavy instead of the SLS. However, this is something that, again, goes back to the politics of it all and the fact that this was driven from Congress. It is something that is still, as yet, up in the air. So we'll see what happens there. I'm excited for either option, really. They're both good ways to get there. It's just a matter of, let's make sure we launch spacecraft and explore this place. Anyway, moving on to some other things out there, because those 4 moons aren't all of them. We also have very faint rings that were actually discovered by the Voyager 1 spacecraft. That's how faint they are. They really aren't noticeable here on the Earth. So if we go out to look at Jupiter when we're done here, don't ask for me to show you the rings of Jupiter, because we won't see them. Again, it took a spacecraft going there to find them, and you can actually see the imaging of it from here. You can see standard image and sensitivity. You can see some nice rings, but as you go further out, you need to increase that intensity 10-fold, 20-fold, 250-fold, or is that 60? Anyway, you get so far out there that you really can't see it. So that's from a spacecraft there. It takes a lot of effort to see these, and each of them are thousands of kilometers wide, and I will note that there are so many other moons out there that it would take way too much time to discuss them individually, but there are a few worth talking about more in detail, and these are some newly discovered moons. They were actually a set of 12 moons discovered last year. These were discovered by a team that, well, they were looking for some other things. I'll come back to that, but they have 2 different types of orbits. That is, when you actually look at an object, say you're looking down on an object from its north pole, if you look down at Jupiter from its north pole, it'll appear to be rotating counterclockwise. Anything orbiting around it counterclockwise is considered prograde. Anything orbiting around it clockwise is considered retrograde. So when we look at these, some of these have prograde orbits while others have retrograde orbits, and all of them take between 1 to over 2 Earth years to orbit around Jupiter. That is how large this system actually is that it actually takes over a year, an Earth year, for some of these objects to orbit around Jupiter. And these moons were either discovered or rediscovered kind of by accident. That is, the team was actually looking out into the far outer reaches of the solar system, looking for what they call Kuiper Belt objects. That is out where Pluto is, and Eris, and all sorts of other things. They were looking specifically for that mythical planet 9 that might be the size of Neptune out there. We'll see if it's out there. It takes a lot of effort to try and find it. But in the meantime, I'm happy they found these things. So these things are really interesting. Here's a nice diagram of some of them. So again, the Galilean moons are here going around in a prograde orbit, as are some of the other moons further out. And then you have a bunch of these other ones that are actually retrograde, going the other way, with some exceptions like this one. At the time of the making of this image, this was a proposed name. But, in fact, 6 of these 12 objects now have nice names given to them, and we'll go quickly through some of these. Again, these are small. They're only about 1 to 4 kilometers in diameter. They're small. If you walked any distance to get here, you probably walked further. But these particular objects, by the International Astronomical Union's convention, end up being named for a relative of Zeus, very often either daughters or granddaughters in this case. And again, Zeus and Jupiter are essentially synonymous. There's some details there that are a little bit more complicated, but that's ancient mythology for you. But the Carnegie Institute, who is responsible for really finding these objects, held a nice naming contest on Twitter. And so let's have a nice little chance to meet these particular goddesses. Again, we'll go through this really quickly, though. First, we have Pandia. Pandia is a daughter of Zeus and Selene, where this particular one, it had a nice designation. It was Jupiter LXV, or again, that would be 65. It was discovered really in 2017, 3 kilometers in diameter. And this is an important note with regards to these. If you ever come back and look at a whole bunch of different moon names of Jupiter, it's in the Himalaya. Himalaya. Yeah, say that 5 times fast. Himalaya group, which really means they actually give them names that specifically always end in A. So this is actually something you'll see frequently. So when we go to the next one, guess which group it's in? Yeah, this is Ursa. It is actually the sister of Pandia, and it had its original designation thusly when it was also discovered in 2018. And it is a little one, about 3 kilometers in diameter again. And again, the A, it's in the Himalaya group. And thus we can know that this one, Irene, is in a different group. That is, Irene is actually a Greek goddess of peace, and Pax is the Roman name. So if you've ever heard of the Pax Romana, it is a time of peace in the Roman Empire. That particular name, again, it's coming from this, Pax. But Themis is her mother, and she was the one who really might be where we actually get that picture of justice holding those scales. But the particular designation here, it's an interesting one. It was originally discovered in 2003. They kind of lost track of it, and then they rediscovered it with this particular team. So this one also about 4 kilometers in diameter, and it's in the Carmi group, which is really a group of, again, really odd ones that are going the opposite direction of other things. So this is a retrograde moon. And then we got a fun one right here. I'm pretty sure our docent who helped me with some of these slides, Ron Treat, was really just trying to test my ability to say some of these names. So this is Philophrosine. Yes, Philophrosine, the ancient Greek spirit of welcomeness, friendliness, and kindness. What a lovely little goddess name here. But then we got Hephaestus, and the Roman equivalent Vulcan. Yes, this particular one would be a reference the term Vulcan, again, it's not just something from Star Trek and live long and prosper and all that. It is actually something from really more ancient mythology, hence the term volcanism and volcano are all from that particular root there. And then Agalia, youngest Grace, and granddaughter of Zeus. Again, this is another one that was lost in 2003 and was rediscovered with this particular set. It's a small one, only about 2 kilometers in diameter, and it's in the Pasiphae group, made up of, again, irregular retrograde moons. All right, then we got another one. Yeah, I'm serious. Ron was probably just trying to test me here. So this is Eupheme. Eupheme, ancient Greek spirit of good omens, praise, and applause. All right, that's great. Hopefully she visits us tonight. But yes, this particular one, again, we've got a Roman goddess, or Roman god Vulcan, and youngest Grace. Again, this would make this particular one a sister to Irene, and was also lost in 2003 and rediscovered. And this one's, again, a very small one. They all are. And it's actually in a different group, though. It's the Anike group. And so it's another set of those retrograde ones, those ones moving in the opposite direction. And then we have an odd one out in that outer regions. This was the one that was referenced in that particular picture with a preliminary name that eventually got accepted. This is Valentudo, the Roman goddess of health and hygiene, and great-granddaughter of Jupiter. And this particular one was actually discovered in 2018, but it was discovered in 2016, announced in 2018, and it's a little one, about 1 kilometer in diameter. And this is a key thing about this one. This one is actually going prograde, where most of the other objects are going retrograde, which means that there's a slight chance that it could eventually have a dramatic collision with another object. So how do we end up with moons going opposite directions around Jupiter? Well, what's expected is all of those retrograde objects were likely actually captured by Jupiter. They happen to get too close to it and get pulled up by its gravity and brought into its orbit, just like they expect to do with the Juno mission. Get it over just close enough and get scooped up with it. If you get slightly different directionality on that, you can actually have something going the opposite direction around that planet. So how then can we say that Jupiter is the king of the planets? Well, it should be obvious by a lot of the things we were talking about. It is, again, the most massive planet in the solar system, more massive, again, than all of the other planets combined. It has a tremendous gravitational pull, and that, again, influences not only the way the moons actually work, not only how they move, but their actual structure themselves, and it can actually influence the entire regions of the solar system, including the asteroid belt. One of the reasons that might be there is because the asteroid belt is in a specific resonance with the orbit of Jupiter, actually causing it to, as Jupiter swings on by, tug things in different directions, helping to prevent a larger body from coalescing from all the material in the asteroid belt. So that belt may be the responsibility of Jupiter there, and it can also redirect and destroy comets. One really famous example of this is actually Comet Shoemaker-Levy 9. This one was literally torn apart by Jupiter's gravity, and it actually swung back by and hit the planet in July of 1994. This is the famous string of pearls image that was taken of that comet. After it was torn apart, it actually looked like a whole bunch of little comets, each with their own tails, but they were moving in a very specific direction right into the planet Jupiter, where it left some pretty dramatic scars. But again, because Jupiter doesn't have a solid surface from which to leave a crater, the actual passage of time has allowed those clouds to swirl around and mix away those scars. They really aren't that noticeable or even there at this point. So it's a really neat thing to actually see how a gas giant like this, well, it can scoop up some of these otherwise potentially dangerous bits of debris moving through the solar system. And there's another dangerous thing, though, about Jupiter, and that is its magnetic field. This data from the Juno spacecraft shows a really dramatic set of magnetic field lines around Jupiter. Jupiter, after the Sun, is the largest and most powerful magnetic object in the solar system. And you can actually see it doesn't have a simple bar magnet shape. We actually had a nice pole up here, but there is a bit of a pole down here, but there was a nice thing referred to by some, that is the people working on it, as the Great Blue Spot. Let's get that to show up again because I want to make sure you see that. It'll swing right around here in a second. There it is. So that is the Great Blue Spot, as it were. It's not actually blue. It's actually just referring to an area where magnetic field lines are going into Jupiter right at that point. They're coming out of the top and back down in it. And this particular shape is worth noting because magnetic fields have a way of influencing charged particles. For example, the way it actually influences charged particles is as a particle goes through a magnetic field, it will be turned to the side and can actually be driven into going around very specific paths and forming belts of these particles. These are referred to as the Van Allen radiation belts, and here's Jupiter's set of them. See it doing a little dance there? Yeah. Anyway, this particular view, we actually have, based on the magnetic field of Jupiter, these particles get trapped around it, and they make the environment in these areas absolutely stunningly inhospitable to life. And so there are a few of the Galilean moons in this particular area, and as such, we don't really want to go to Io. I don't recommend it for your next beach vacation. And in fact, this is what influences Juno's orbit. What Juno is doing is it's again coming right through over the North Pole and skimming right above above the atmosphere of Jupiter, getting as little of this spending as little bit of time as possible in this radiation belt and zipping off to the other side to loop all the way back around again. And likewise, the Europa Clipper will be doing a similar thing to actually spend a little bit less time in the highly irradiated zone around Jupiter. So these are really important things to take into account when trying to explore this world. But it is also worth noting, though, well, is Jupiter actually going to be, if it's the king of the planets here in our solar system, is the king of all of the planets we know of? And, again, in our solar system, sure, but when we look outside our solar system, not so much. There's actually a number of other things worth noting. We've found over 1,200 gas giants outside of our solar system, and many of them are actually significantly more massive than Jupiter, even some more than 10 times as massive as Jupiter. Eventually, you get to the point where you actually would have planets getting close to the point where we have trouble distinguishing them from really low-mass stars. We're still working on really understanding that fine line to actually really truly make sense of where the true king of the planets would be. But, so what shall we then say of Jupiter? I still think it's a wonderful place. I still think it is a gorgeous planet. Well, with that, I want to say thank you all for being here. Really appreciate you being here.